Good morning. I'm going to get started in about 1 minute here. Hey, Courtney. Um, I saw you on the Wolfcast the other day, and you look different now. Like you look 1 year older now. I almost didn't recognize you. Hope you're doing well. My spring break was pretty good. Um, oh, I forgot to talk about that. Yeah, my parents visited from Washington, and we went to the horse races at Santa Anita Park on Saturday. So I had a fun time betting on the horses, and otherwise, pretty much just hung out and relaxed, I guess. Um, all right, class, I'm going to go ahead and get started. Um, so, what we're going to do today is we're going to start talking about electric circuits. Okay. Um, and so the the key variables. So the variables that are most used in electric circuits are um, potential difference, electric potential difference, by the way, this lesson is going to be more or less a review of last year's circuits, and then in the next lesson this week, we'll start talking about new circuit things, but I just wanted to remind you. So electric potential difference is one of the key variables. And so that is delta V. But in the context of circuits, because we're pretty much always talking about electric potential difference, we just call it V. All right, so even though it means V final minus V initial, we will write it as just straight up V most often. And so, all right, and then the other variable is electric current, which you are familiar with from discussion of magnetism. Electric current is the rate of flow of electric charge, and it's denoted by I. All right. So V and I are the most important variables in electric circuits. Now you could think about V as voltage, and in circuits, I will refer to electric potential difference purely as voltage. I forgot to say that. Okay. So voltage is basically, in the context of circuits, you can think about voltage as a force causing current to flow. Okay, so voltage is the cause, and you could think about current as the effect. Okay, so voltage is the cause, current is the effect. So you can't have anything happen in a circuit unless there's a voltage somewhere. Once there's a voltage, then stuff starts to happen. All right. So let me show you how to draw electric circuits. Um, okay. Uh, so um, just a straight up line is a symbol for a wire. A and wires can of course have branches. So if you can draw something like this. This is a wire that is splitting in two. This is a wire that's splitting in three. So these are wires with branches. Wires can bend, so you can have wires that turn. This is a wire with a bend. Okay. There is a battery. Which is drawn like this: long line, short line, long line, short line. And the reason that that's a symbol for a battery is that the first batteries were made out of stacks of two different materials. Okay. And so you would have stack A, or you'd have A, B, A, B, A, B, and they would make this stack, and that is what the first batteries, how they were built. And so this is sort of representing those stacks of two different materials. Okay. And the longer line is the higher potential side. Okay. So normally with a battery, you would write the voltage that battery provides next to it. So you could have, for example, a 6-volt battery. Okay. And so what that means is that the battery is going to increase the voltage by 6 volts. So for example, if the electric potential here was 8 volts, then after you go through the battery, the potential here is going to be 14 volts. Okay, so this is telling you that the voltage, the potential difference that the battery creates. Okay. Batteries, they push current out of the positive terminal. Okay, so batteries push current out of the positive terminal. So if you have a battery that looks like this is the positive terminal because that has the longer line. So the current is going to come out that way. All right, that's the sense at which the current comes out. All right. I will also use the symbol for just an arbitrary voltage source. So this symbol represents a battery in particular, but there are ways in which there are things that behave like batteries that aren't batteries. Okay, so for example, a power outlet provides a source of voltage, but it's not a battery. Okay, so if you have something that is providing a voltage, but you don't want to specify what it is, it could be a power outlet, it could be a solar panel, it could be a battery, then you just put a circle with a positive and a negative. Okay, and so this would push current out the positive terminal just like a, a battery. Okay, and again, you write the voltage of that particular source right next to it. The other device that we're going to talk about today is called a resistor. Okay, and the symbol for a resistor is a jagged line. And basically, a resistor resists current flow. So a resistor will prevent the current from being too extreme. Or resistors oftentimes represent other objects. So sometimes a resistor is intentionally put into a circuit in order to control the amount of current that is flowing. All right. Other times a resistor is representing something else. So, for example, from the perspective of a circuit, a motor might look just like a resistor. Okay. So it's how does it behave, even though that thing is doing something else in the external world outside the circuit. From the perspective of the circuit, all it's doing is it's resisting the flow of current. Resistors have a value called R, which is the resistance. Okay, and so the units of resistance are called ohms, because the person who first studied resistance, his name was Georg Ohm, and that has the symbol capital Greek letter omega. Okay. Now, so let's suppose that current is flowing through a resistor. As a result of that, the resistor is going to develop a potential difference. It's going to develop a voltage. But the important point is that resistors, the positive side of a resistor is opposite what it is for a battery. Okay? So if you think about a battery or a source of voltage, the current goes out of the positive terminal. But for a resistor, the positive side is the side that the current is going into. Now, why is that? It has to do with energy consumption. Okay, batteries are putting energy out into the circuit. So if something is putting energy out into the circuit, then the positive side is going to be the side that current comes out of. But resistors don't put energy out into the circuit. They take energy and either turn it into heat or do something useful with that energy. For example, a light bulb. If this resistor was representing a light bulb, the light bulb produces luminous energy. Okay, so that's useful to us. So or a motor is consuming that energy and turning it into motion. Okay, so if something is consuming energy from the circuit and doing something with it, then the current goes into the positive side of it. Positive side being the side that's at a higher electric potential. Okay, so with resistors, the potential difference, aka voltage, and the current are all related according to Ohm's law. All right. And it says that the potential difference across a resistor is equal to the current times the resistance. So that is one of the most fundamental circuit equations, probably the most fundamental circuit equation. Okay. So what this says is that, we could rearrange it. This also expresses sort of the cause and effect relationship. The bigger the voltage is, the larger the current. Okay. The bigger the resistance is, the smaller the current for a given voltage. Okay. More resistance means less current is going to flow. So let's draw the most simple circuit that we can draw. All right. So the most simple circuit we can draw is this one. And so let's say that this is a 12-volt battery, and this is a 3-ohm resistor. Now, because this is the positive terminal of the battery, the current is going to flow out. It's going to go around this corner. It's going to come down here, and it's going to enter the resistor, and then it's going to come out the resistor, go around, and go back into the negative terminal. Okay? Now, because a resistor is using up the energy, its resistance, or its positive side, is going to be that side, because that's the side that the current is going into. And so if I wanted to know how much current is going to flow, all right, what I would do is I would apply Ohm's law. So this battery is providing the resistor with 12 volts, and the resistance is 3 ohms. So then dividing by 3, we get that the current is 4 amps. So that's how much current is going to flow in this circuit, and it's going to flow in this sense because that is the positive terminal of the battery. Okay. There's also a nice equation that allows us to calculate the power output of the battery, and that equation is P equals I times V. So the rate at which the battery is putting energy into the circuit is current times voltage. So the power output of this battery, well, we know that the battery is outputting 4 amps. And we know that the voltage provided by the battery is 12 volts. So this battery is outputting energy at a rate of 48 watts. So 48 joules per second is coming out of this battery. And the way circuits work, sort of conservation of energy in circuits, is that because 48 watts of power is 48 joules per second is going out of the battery, the resistor is consuming or using 48 joules of energy per second. So it's either taking that energy, if this is representing a light bulb, then the amount of light that's coming out there, that light is carrying 48 joules of energy per second away from the light bulb. Or if it's lifting something, if it's a motor that's lifting something, it's lifting it up, adding 48 joules of gravitational potential energy every second, something like that. Okay? You can combine batteries. So let me talk a little bit about that. Well, actually, let me talk about the two basic types of connections. Okay, so there are two really common connections that appear in circuits. Okay, so common circuit connections. all right? And the first common circuit connection is what's called a series connection, okay? And a series connection, basically you can go from A to B without the wire branching. Okay, so let's suppose I have resistor 1 and I have resistor 2 connected like this. Then these two resistors are in series because I can go from resistor 1 to resistor 2, and the wire in between them doesn't sprout off in any other directions. Okay, so this is series. All right, these are in series. It doesn't matter if the wire bends. The wire can bend. That is still series because even though the wire bent, there is no branching off of the wire. Okay. All right. So let me draw you something that is not in series. If you had 1, 2, and 3, these 1 and 2 are not in series. All right, because if you were to go from 1 to 2, see how in between them the wire branches off and it goes in that direction. So this is no longer in series. All right. So it turns out that if you have two resistors in series, it's equivalent to a single resistor from the perspective of the battery. So the battery, all the battery is doing is trying to push out electric current, and it doesn't have the ability to look at the circuit from a bird's eye view. It's just trying to push out as much current as it can. And so from the perspective of a battery, two resistors in series looks just like a single resistor, which I'll call R sub S. Okay. And R sub S is equal to the sum of the two resistances. Okay. Important fact about series: you can have two different things can be in series. Two different things can be in series. So for example, you could have a resistor in series with a battery. That's we would still say that they are in series. Incredibly important thing. Series things have the same current. So the voltage of things that are in series in general will be different. So the voltage that resistor 1 gets is going to be different from the voltage that resistor 2 gets, but they will get the same current if they are in series. So that is incredibly important and useful if you're analyzing circuits. Okay. So let me tell you about the second way that things can be combined in circuits. And these aren't the only two ways, but these are the most common two ways that two things might be connected to each other. That's called parallel connection. And a parallel connection looks like this. So the wire splits into two parts. there's a circuit thing in each part, and then the wires come back together. So I would call these different branches. So the wire breaks apart into two branches here, R1, R2, okay? And there's only one thing in each branch in order for it to be um, in parallel, okay? So one way you can tell, a nice way to tell if two things are in parallel, is we can imagine a circuit is almost like a trail system. You know, it's like if you go to the Claremont Wilderness Park and you walk on the trails, you can branch off into different trails. Okay, that's just like an electric circuit. Okay, and just like in the Claremont Wilderness Park, you can do a loop. You can come back to where you started. Okay, so just like in circuits, we can imagine walking around the circuit in a loop. Okay, and so you can see if I walk around this loop here, all right, this loop has only those two resistors. So that is how you tell if two things are in parallel. Okay, you can do a loop with only those two things. Then they are in parallel. Okay? So it has nothing to do with the direction that the resistors are pointing. You can have resistors pointed in different directions and still be in parallel. So for example, if I had, something that looks like this, these two resistors are in parallel. Why? Because if I walked around this box here, it only has those two resistors in it. So those two things are in parallel. But if you had something like this, for example, where you have so you have 1, 2, 3, you might be tempted to say that 1 and 2 are in parallel. After all, they're pointed in the same direction. But if I go around this loop, all right, this loop, it has resistor 1 and 2, but it also has resistor 3, so they're not alone. Okay? So two things that, all right? Here is a really weird way of if we thought about this, this is actually in parallel as well, right? Because the reason that it's in parallel is because I can do a loop, okay? And in that loop, there's only these two resistors, so they're in parallel. These two resistors are actually in parallel and in series simultaneously, because I can do this loop with only those two resistors, and also I can go from resistor 1 to resistor 2 along this path, and there's no forks in the wire along that path. Okay? So they are in series and in parallel simultaneously, so that can happen. Notice how these two things are in series, but because there's this path, but there's another path that does have forks. So if you go that way, if you go around this way, you go from resistor 1 to resistor 2, and there are two forks in the road. So it doesn't mean that there's only paths with no forks. It means that there just exists one path with no forks, and they are in series. If there exists one loop where there are only those two things, then they are in parallel. Now, it turns out that from the perspective of a circuit, two things being in parallel means that they're equivalent to a single resistor. Two resistors in parallel is equivalent to a single resistor, which I will call R sub P. And the formula for R sub P is 1 over R sub P equals 1 over R1 plus 1 over R2. Okay? So it's the same equation as for series, but it's just you replace every resistor with 1 over R. So just like with series connections, two different things can be in parallel. Okay, so for example, you could have a resistor in parallel with a battery. That's completely valid. Like that. Okay. Critically important thing about things that are in parallel. Parallel things have the same voltage. This is incredibly important. So because resistor 1 and resistor 2 are in parallel, their V values in Ohm's law, their V value in Ohm's law will be the same. Okay? Their V value will be the same. Parallel things have the same voltage. So I like to combine these two things into a mnemonic to help you remember. It's called SIPOV. It's a horrible mnemonic, but it's so bad that you won't forget it. So that's why I use it. Series things have the same current. Parallel things have the same voltage. So you always want to have that in your head when you're doing circuit analysis. All right, so this is going to be a 2-pager. More like a 1.5-pager. All right, so I did want to talk about combining batteries. Okay. Because sometimes you have a circuit that has more than one battery. And so if batteries are in parallel, they must have the same voltage. Okay. So you can have two batteries that are in parallel with each other, so that will look like this. And so this would basically, each battery is able to provide current, so you can get more current because you have two batteries side by side pushing current into the circuit. So that's why you would do that, why you would put parallel batteries together. But they must have the same voltage, okay? So they have to be, for example, 3 volts and 3 volts. And they have to have the same their positive sides have to be connected to each other, okay? If you don't do this, then you're asking for trouble in the circuit. Obviously, you could take a 12-volt battery and a 1-volt battery and you could put them in parallel, but unpredictable things are going to happen if you do that. So it's not done. All right. So that's an important point. So you would never have something like this. So this is two batteries that are in parallel, and they're both 3-volt batteries, but one is pointed down and the other one's pointed up. That's not good. That's really not good. This is something that can happen by accident if you are if your battery dies in a car and you're getting a jump start. If you connect up the wires wrong, you can have this kind of a situation, and that will very easily start a fire. So that's very bad. And you would also never have a situation like this, where you have two batteries that have different sizes in parallel. That's not good. Okay. And then if you have series batteries, then they add up. Oh, and by the way, parallel batteries are just equivalent to whatever their parallel value is. Okay, so if you have parallel batteries, then and they're both 3 volts, then it's equivalent to a 3-volt battery. But it's a 3-volt battery that is going to be able to output twice as much current. Okay. Series batteries add up the voltages. So, for example, if you had a 12-volt battery and then it's in series with a 3-volt battery, so they're stacked with the same polarity, then this is going to be equivalent in terms of its performance in a circuit to a single 15-volt battery. All right. And you could even, I don't know why you would do this, because you're basically making the batteries fight each other, but you could also do something like this. Okay. So you're connecting the negative terminal of a battery to the negative terminal of a battery. Let's say this is 3 volts and this is 12 volts. Okay. So because the 12-volt is bigger in size than 3, its positive terminal is going to be the positive terminal of the overall thing. So this is going to look like a 9-volt battery that's pointed in this direction. All right. So I don't know why you would do that, because that's just making the batteries fight each other. It's kind of wasteful. But you do often see batteries stacked in series. That's what's happening when you put in multiple batteries into like a TV remote. Okay, you're putting those batteries in series with each other to achieve a certain voltage for the circuit. Okay. So let's do a full problem. All right. So we're going to do an example just to show how all this works. So we have two batteries like this. And then a resistor and resistor and a resistor and a resistor and a resistor. Actually, let's say 2 resistors. Okay. So let me give these some numbers. So let's say 10 ohms, 5 ohms, 20 ohms, 20 ohms, 8 ohms, 3 ohms. Okay. And then let's say that this is a, this battery is 20 volts and this battery is 6 volts. Okay, so what we want to do is we want to identify combinations of resistors. And by the way, what we want to know is what is the power output of the batteries. All right, so what I'm going to do is I'm going to try to identify combinations that I know are either in series or in parallel. So I see that these two are in series because I can go along this path and I can get from one resistor to the other without the wire forking. Okay, so then I'm going to use my series resistor formula, which is R sub S equals 20 plus 20 equals 40. So these two are equivalent to a single 40 ohm resistor. Then I have my batteries. They are also in series, so they're going to combine. The 20 volt is bigger, and they're pointed in opposite directions, so they're going to subtract in voltage. So this is a stupid circuit designer. I designed the circuit. Oh no. So that's going to be 14 volts going that way. So now I'm going to redraw the circuit. So I took these two and I replaced them with a 40 ohm. And I hope you can forgive me. I'm not going to do units just in the interest of time. All right. And this is 14 volts. So now I can see that these two are in parallel. Why? Because I can go around this loop and only encounter those two resistors. So now I'm going to use the parallel formula. So 1 over R sub P is 1 over 8 plus 1 over 40. So that tells us that R sub P is equal to 6.7 ohms. So now I'm going to take those two and I'm going to replace them with a single 6.7 ohm resistor. Okay, now I can see that the 6.7 and the 3 are in series with each other because they are connected along this path which has no forks. So R sub S is going to be the sum of the two. That's going to be 9.7 ohms. So I can redraw the circuit, replacing these two with a single resistor. All right, and now it kind of gets tricky, but it actually turns out that the 10 and the 6.7 are in parallel. How do I know that? Because if I go around this outer path, see how that outer path only has these two resistors along it. So that means that those two are in parallel with each other. So I have 1 over R sub P is 1 over 10 plus 1 over 6.7, which says that R sub P is equal to 4.1, or actually just about 4 ohms. So now I can replace those with just a single resistor. Then I can see that the 5 and the 4 are now in series with each other because they connect along this path that has no forks. So R sub S is 9 ohms. So the entire resistance that this circuit sees is 9 ohms. Or the battery C is 9 ohms. Right? Because we just got it down to one resistor. So we use the laws of combining resistors to get it just down to one resistor. Okay? Once we have it down to one resistor, we use Ohm's law. So V equals I times R. The voltage is 14 volts. The resistance, the total resistance is 9 ohms. So we get 1.6 amps of current. So that means that the batteries are outputting 1.6 amps. It's going to go out this way. All right. Now, if we think about it, referencing the original picture, the current is going to be coming out this way. It's going to hit this junction. Some of the current is going to go this way. Some of the current is going to go this way. This current is going to hit the junction. Some of the current is going to go this way. Some of the current is going to go this way. Then it's going to come back together right here and go that way. And then this current is going to join with the current that came up this way. And then they come back together right there. So that's kind of, so the current that goes out of the battery is not the same as the current that each element gets, because the current is splitting as it passes through the circuit. So we have 1.6 amps. Then we use P equals IV. Current is 1.6. The voltage is 14 volts. And we get 21.8 watts is the power output of the batteries. All right, so that is my lesson for today, and I will see you in the Zoom room.